that the existing systems were okay as long as they had sufficient hydraulic capacity. The fourth and very fundamental, but probably least justifiable assumption that they made was that these area density curves for the different commodity classes would be parallel to each other. Now, they also needed to come up with what would be characterized as acceptable performance. They needed the pass-fail criteria. So, like the committees do, they sat down and said, all right, what are our pass-fail criteria going to be? Said, well, all right, we want to limit fire spread. So we'll say we don't want the fires to damage product in the main rack to a distance in excess of 12 feet from the point of ignition or ignite combustibles in the target piles. So basically, they wanted, kind of 12-foot wide, 20. See, is that? I'm not sure if that's interpreted to be on either side or not, but a 12 to 24-foot wide burned area, nothing more than that. Total water demand not to exceed 1,500 gallons a minute. Air temperatures at the ceiling greater than 1,000 degrees for no more than 5 minutes within any 400 square foot ceiling area, and the rack steel integrity must be maintained. That seems reasonable criteria. When they ran all the tests they ran, and they came up with their revised pass-fail criteria, which said, and I stated it did not, because this wasn't a proactive determination of what pass-fail should look like. It was, we have all this data, we better figure out how to make some of this stuff look like it worked. They said the fire did not extend beyond the first row of commodity in the target array. So that, and we'll have some pictures of it exactly. I mean, you can burn on the target array all you want, as long as you can burn all the way through the target array, that was okay. Fire did not burn the entire length of the main array. So you could burn 99% of the main array, but as long as you didn't burn all the way out to the ends, that was okay. And the fires didn't open sprinklers in the last ring of the test facility, so you could operate, almost 100 sprinklers. But if you operated around about 100, you'd start to get into that last array. They decided that was probably a few too many. So they ran all these tests, and they're the critical ones shown here. And this is sort of where they fall on the curves. The baseline curves. And what they did was they started with class 2 commodity. They said, we're going to run these points on the class 2 commodity. They ran, you see down here it's about 375 density and it operated 1,800 square feet. And a couple of tests up here, about 3.0 density, and those were 4,500 square feet. And they had a couple of tests that were way off the curve. Well, when you look at it, this point down here isn't on the curve today. This point here is just barely on the bottom of the curve. And then they have these 2 points there, which are sort of in the middle of the curve. So the class 2 curve has 3 data points that actually lie on it. And these other ones that they use to draw it, but then they cut off. I don't know if anyone wanted to really design for a 10,000 square foot operational area, so they decided that they would just cut it off. So that was fine. And then they had to look at class 3 and class 1. So they ran one test for the class 3 curve, which wasn't actually on the curve that we use today, but they said, well, these curves are parallel, so we run that one point, draw a line parallel, that gives us our curve. They assumed that if I guess they just did it numerically, if 3 is 1 away from 2, then 1 is the same distance away from 2. So if the class 3 curve is 12% high, then the class 1 curve is 12% lower. And then they did the class 4 curve, and we'll talk about that because there's all kinds of problems in there. But this is where the basic curves came from. And in total, there are 3 points that actually lie, 3 tests that lie on the curves that we now, the designers should figure out how you're going, well, is that a 0.04789 or an 0.04793? Well, there are those 3 points that were on the curve, but let's actually look at the most successful test that's on the curve. That's one of the class 2 curve, right in the middle of that curve, test number 65. I put this up just to show you that we really have the actual data, but since you can't read that, I did it this way too. 22% of the boxes are consumed. The aisle jump across the east and the west aisles. Okay? That's not great, but not terrible. Rack steel above 1,700 degrees Fahrenheit for 22 minutes. Steel columns above 1,000 degrees for 6 minutes. gas temperature is above 1,000 degrees for 15 minutes, and 45 sprinklers operate. Well, this would, today, if you took this data set, went to UL and said, I'd like to get this listed, they would just laugh at you and send you home. But this is the underlying data for the curves that are in the code curve. So let's look at this parallelism thing where they developed a class 3 curve from this class 2 curve. And they used what we call the hallmark test at one point. And again, here's the actual test data, but I pulled out the relevant points. 165 degree sprinklers, standard response, 10 foot by 10 foot spacing, 0.3 gallons per minute per square foot density, 20 foot high storage. All of these tests were done with 20 feet of storage. And the hallmark commodity was literally commodity that was donated by Hallmark. And it was cards and paper plates and cups and in a box. You know, cartoned, combustible commodity, no plastics. And I wanted to point out this fire chronology because I want to compare the chronology they show here to the chronology we see when we do class 3 today. So let's look at it. 45 seconds, flames reach the top of the first tier. 2 minutes, flames are at the bottom of the second tier. 5 minutes, flames are still at the bottom of the second tier. At 6.5 minutes, the box fell apart, the napkins fell out of the box, resulting in a, and I'll quote, vigorous eruption of flames. And that really set things off so that by 7 minutes we had flames at the midpoint of the third tier. Here's the results from that test. 70 sprinklers operated over a 20-minute period. The ceiling bar joist got to 275 degrees, which is fine. Rack steel temperatures at 1,000 degrees for 26 minutes. Steel columns at 1,000 degrees for more than 30 minutes. Gas temperatures at the ceiling above 1,000 degrees for more than 17 minutes. Again, not a stellar success. And actually, if you look here, this is the extent of the damage. In the Hallmark test, on the primary array was burnt out entirely to the north end of the array, and about 3/4 or more than 3/4 of the way down to the south end of the array, and it jumped both aisles onto the target arrays. It essentially burned out almost all the commodity that was there. But you could take that point, 70 heads, those 70,000 square feet, or 7,000 square feet, excuse me, and 3.0 density, and put it on the graph paper and get out your ruler. You add that class 2 line, take that point, draw that class 3 line in, and that's what they did. So said, looked at that and said, well, from there to there is 12%, so class 1 is 12% the other way. That's what we'll do. Now, it's not that they thought that this was really great science. Remember I said that money was an issue? They had a bunch of tests, spent the money, did the best they could, now they had to draw curves from it, and so this is how they did it. To this day, there's never been any testing to verify the class 1 curve. That's probably not a big deal, but it's important to note that there hasn't been that test. Here's a modern class 3 test. It's a little bright. Here's a modern, here's the Hallmark timeline. I wonder if someone could just dim the lights a little bit. It might be helpful. There we go. This was done just last year. It's class 3 commodity at UL. Standard laboratory class 3 commodity. In this case, it's 30 feet of storage instead of 20 feet of storage. But we're only going to actually care about the fire growth up to the third tier, so I don't think it makes that big a difference. Here's 30 seconds in. I've got a little timeline here just to give you a hint. Now there's always a little variability between when the fire, oh wait a minute, flames at the bottom of the second tier at 45 seconds. It was 2 minutes in the Hallmark test. There's always a little variability in this sort of jump from the first to the second tier. It just depends on how that initial fire develops. But usually once it gets into the second tier, it's extremely repeatable. So flames in the middle of the third tier at minute 15 in the Hallmark test, it was 7 minutes to get there. And then all the rest of this I'm going to show you, this guy, we're already this far into it, we just must see it out to the end. These are Ultra K17s. Now this is actually a dry test. So what we'll see, and it's with 286-degree heads, high temperature heads, but it's a dry test, so you'll hear the head go off, and then there'll be a period of delay of about 25 or 30 seconds before the water is actually discharged. Just a side note, with 286-degree sprinklers, we usually start to see operation in the first ring once the flames have hit the ceiling and extended along the ceiling just about out to that first ring. Standard response 286-degree head is a pretty slow device. There's the first operation. 5-foot clearance, so it's 30 feet of storage under a 35-foot ceiling. I think this is 25 or 27 seconds delay on the water delivery. If you listen close, you can hear the heads operating. And I think in this test, over that delay period, we operated 16 heads. And it works fine. You can watch it through sort of the lens. Control those sprinklers. Doesn't jump to the target array. Doesn't travel out to the ends of that. Push down too quick. Usually when you see this phenomenon, this smoke getting driven down and the visibility going before, that means you've pretty well got the test under control. When it stays real bright, it tends to be indicative of potential failure. So control those sprinklers, visibility. Yeah. So a bit of a hallmark test was boxes of paper plates and napkins and things. This is the standard class 3 commodity. It's a bunch of paper cups and compartments in a cardboard box, nothing fancy. But it burns very good, primarily because the fuel density is low and the surface area is high. So it's a big box of air, fire just burns up through. But it's supposed to represent a class 3 commodity. The laboratories have decided that this is a class 3 commodity. Well, the test that we use to develop a class 3 curve doesn't have properties that look anything like this. So either this commodity is wrong, or the class 3 curve is wrong, or maybe none of it's wrong and we've just gotten lucky. It's definitely one of those three things. So things get even more interesting when you go to do the class 4 curve. So they ran a test number 78 at a relatively high density. It seemed to work pretty well. They wanted to run another test at a lower density. So they ran a test 99, but because they didn't think they didn't have enough water supply capacity at the test lab to actually get their design density, so someone had the brilliant idea of installing the sprinklers on smaller spacing. They installed them on 50-foot spacing. Well, they didn't think about skipping. So what happened was they put these sprinklers on 50-foot spacing, lit the fire, fire went up, started setting off heads, and they skipped a whole bunch of heads, but they still managed to operate 82. They said, well, what the hell are we going to do now? So what we did was they drew a big box around all the area that was operated, and then they counted all the sprinklers inside that area that it operated and figured out what that total flow rate was, and then divided it by the area and ignored the heads that didn't operate and just says, well, it doesn't really matter how many heads operate in the area or why they operate. It's just we put 1,000 gallons a minute into this box, or I think it was 2,700 gallons a minute, into this box, and so that gives us the density of whatever it was. I think it was a point, where is it? It's here somewhere. Yeah, 0.6 density. So if I go back, I won't go back. So we'll see that curve again. So when you look on that curve, there's test number 78. It's way up on the curve. There's test 99 that's sort of nowhere on the curve, but they said that through this mathematical backflip that was a successful test and validated that curve. And so really, to this day, the class 4 curve doesn't have any points tested that are actually on the curve. But they assumed that was parallel to the class 2 curve as well, so that's how they're able to draw in the actual curve. Now another important point is the repeatability of these tests. Because you've only got a couple of tests that you're drawing your curve from, Well, how do you know how wide to make that line? How thick should that line really be based on those data points? So there was some tests run that were repetitive tests, and again, I blew it up for you to see. And they played with some of the variables. They started with a grind sprinkler, 100 square foot spacing. This is all class 2, 20 foot of storage. And a 12-inch flue. They operated 25 heads. They said, okay, let's try a 6-inch flue with a Viking sprinkler. So at the time, they were assuming the sprinkler doesn't matter at all. It's just pick a sprinkler, any sprinkler. It's just the density that's important. So let's use a Viking sprinkler and a 6-inch flue. They opened 38 heads. They said, it must have been changing the flue. Excuse me. Let's take the Viking head, move the flues back out to 12 inches, run that test again. They operated 36 heads. They said, so let's go back to the first one that we did, take the grinds head, 12-inch flue, and run the test. They operated 31 heads. So nominally repeating the same basic test, changing only the sprinkler, either gives you a range of variability of, in terms of design area, of 2,500 to 3,100 square feet, if you assume that the sprinkler matters, or if you're working under the assumption that they were working under was that the actual device doesn't matter, it's somewhere between 2,500 and 3,600 square feet is what you should design for 0.3 at a 0.3 density. They didn't include any of this data in the development of the curves, they just drew curves. But this lack of understanding of the uncertainty in the actual test detracts even more from the actual predictive value of those curves. What we later found out is that variations in the performance of the actual sprinkler are extremely important to these results. So here's what they wound up with. We've seen this a couple of times already. Here's that test 99. Here's the test 78. 99, we said, well, it's in the right place, so I guess it validates the curve. It's not really on the curve. The density's high, so for this density, it really should only operate. But somehow it worked out mathematically that was a justification point. But what's happened since then? Remember, they were working with primarily 5.6K sprinklers. Well, since then, we've gotten a little smarter. We figured out that actually the sprinklers do matter, that pressure is important, that droplet size is important, that all kinds of parameters are important. Obviously, there's a minimum density that you need to successfully achieve your performance objectives with any of these. You know, if you put an 0.5 residential density on Group A plastics, I don't care what discharge device you're using, it's not going to work. There's a minimum density you need to do the job. But the fact of the matter is that the design of the sprinkler is an equally important variable. And this is sort of where you demonstrate it right in here. And then here's test 74. Test 74, this is just the class 2 curve. And then down here, essentially the same densities are modern sprinklers. And as the orifice sizes go up, holding the density standard of 375, the number of heads you operate goes down. Because the sprinklers are better, we understand how to use them better, we understand the importance of those parameters. The other thing is that when you look at that, you know, as you have relatively minor increases in the discharge density, the number of heads you expect to operate goes up tremendously. Well, when you use larger orifice heads, and as sort of a standard water supply curve, this doesn't really hold true if you've got a perfectly flat water supply, but when you use larger orifice heads, you can take better advantage of the hydraulic capacity that you have in the system when you don't open the full hydraulic design area. So if you take K5.6 heads, you've got to really crank it to churn out 0.45 density, and you operate a small, only 6 or 8 heads, you're not going to push that much water through them, so the hydraulic advantage or the excess discharge you get from just opening that first few is minimal. Now you take a K25 sprinkler operating at a 7 or 8 PSI, designed at 7 or 8 PSI, and operate 4 of them, you may have effectively double your design discharge density when you open that first few sprinklers. That provides tremendous performance improvement. And you can kind of see that here. Here are a bunch of tests with 5.6K sprinklers, and you can see all class 2. And you can see that, let's see, it's 3 low density, you get 45, 48. You go to the 4 or 5 density, you get down to 7. Density goes up, performance does get better. But pushing a 4.45 density through a 5-6K sprinkler ain't so easy to do. Then you get into ELOs, and we found out at 0.3 density you operate 55 heads. Well, that may mean that that 0.3 density just really isn't adequate for that challenge. 40-55 is sort of close to the 45-48 up here. We go up to a 0.37, you operate 9. We went up to a 0.45 to operate 7 here. Go up to a K17, operate 4 at 0.44, and I think the best one is at the 0.37 here, so we have a 375, we operated 18. We had a 375, we operated 9 with the ELOs, and with the EC25s, we operated 4. All same fire, same everything. The only thing that changed was the sprinkler. So that this idea that density is a fundamental variable doesn't really hold water, because it really does depend on the device you use to generate the density. And I don't think this surprises anyone that's been involved in these sorts of tests. Well, of course, the original goal of this program wasn't just to develop those baseline curves. They wanted to have a methodology to cover all these different things, ceiling heights and aisle widths and whatnot. So they started to look at aisle widths. But again, they didn't have a lot of money, so they committed the classic experimentalistic mistake of changing 2 variables at the same time. They had 8-foot aisles with standard pallets, and then when they went to do some 4-foot aisle tests, they said, we'll do 4-foot aisles and we'll do slave pallets. And what happened was, they went from 45 sprinklers to 89 sprinklers at one density point. It's test 65 and test 90. It's these 2 right here. So this one. Then the higher density point at 375, they went from 18 sprinklers to 55. They said, uh-oh, what are we going to do about that? So what they did is they said, well, roughly, this is about a 40% increase in design area, so we'll say half of that was caused by the slave pallets and half of it's caused by the aisle width. That's how we'll do it. They just split it in half, divided the penalty 50-50. Then ran the test with just one or the other, didn't have the money, and that's where it is. And then that's where you get this 20% higher curve when you have 4-foot aisles. And then, we'll look at the actual language in the standard today in a minute here. I wanted to point this out. Again, when we looked at this data before, 56% of the boxes were consumed. This is test 90, the one that operated 89 sprinklers, where they split the baby. Rack steel at almost 1900 degrees, above 1,000 for nearly 20 minutes. Above 1,000, simulated steel column above 1,000 for 16 minutes. Air temperature above 1,000 for 18 minutes. It's like you've seen before. That's what I really wanted to show you. Here's the area of damage. They burned almost to the end of this rack, completely through the first level of target arrays, completely through the second target array, the backing target array. This test is, by anyone's definition, a complete failure, but it's still used in the development of the curves. And not only is it used, it was used to formulate the adjustments for both aisle width and slave pallets. And here's the language today. For aisle widths between 4, and this one's not important, but this is the one I like. We've seen the curve, and then the slave pallets come in, 12, 3, 2, 1, 5, 9. I think this is the 2003 edition. Solid flat bottom, slave pallets, up to including 25 feet storage height. The densities shall be increased by 20%. There's that 20%, and if you ever wonder where that 20% came from, it's half of this test. Half of the penalty they decided resulted from this test. So the other thing we wanted to look at was ceiling sprinkler temperature rating. Most of the tests that were conducted were done with 165-degree sprinklers. Tests 67, 69, 76, and 94 were run to evaluate 286-degree sprinklers. Test 84 evaluated 212-degree sprinklers. So that looks like a reasonably good data set, except they had to throw out test number 67 because they hung little telltales on the sprinklers. And when they hung them, they didn't really figure out how to do it right. And so what happened was the telltales clipped the operating parts of the sprinklers, caused either those operating parts to lodge in the sprinkler or interfere with the spray pattern. So it wasn't really a good test, and they threw it out. Test 76 was, they could compare to test 70s. They had 76 was a 286, test 70 was a 165, but in both tests they operated more than 100 sprinklers. And in test 70 they had problems regulating the pressure, they had some mechanical difficulties. So between operating that many heads and not really having good experimental control, they decided to throw out that one too. So 67, 69, 76 and 94, 67's gone, 76 is gone. And here's what's left. And you all recognize this table. Test 69 is the point used to develop the curve E, which is the single and double door rack, 8-foot aisles, 286-degree ceiling sprinkler, the area reduction allowance. It's that one data point to define a curve. And then curve F is the 165-degree criteria, and there's test 65 that we've seen already. And then, all of this other, obviously there are a lot more tests in this series than I've shown, and they were used to sort of, in a similar fashion, to develop this family of curves. Test 84, when they evaluated the 212s, they saw a 12% increase in sprinkler operation area, and they decided that was basically a wash. And that's why 13 treats 165 and 212s the same. There's no intermediate adjustment for slightly higher temperature ratings. When we combine the two variables of aisle width and temperature, I'm not quite sure where James is trying to go with this one, so I'll muddle through it here. So a 4-foot aisle at 165-degree temperature, we had test 93, which is this one, and test 74, which must be this one. Okay, I see. You know what, I'm just going to skip this one because I'm not sure what he's trying to say. What's, I think, as concerning, if you will, or not concerning, but as interesting as all these other things, is that when you actually go dig down into the details of these tests, what you really see was that these sprinklers tended not to provide very good fire control. Well, in this case, you had an operation at 229, 359, and 557, and then a long time, and then you saw a whole bunch of other operations start to occur. In about 17 minutes, you start to see a bunch more operations. And that means you had an early control event, but then the fire ultimately got away and started to operate additional heads. Now, the main reason that higher temperature sprinklers are extremely useful and for storage occupancies, and the reason that you're allowed to take a design area reduction is because of the nature of the geometry of operations, and that you get quasi-exponential growth where when you operate, the first 4 heads, which is the first ring, is only 4 heads. If you go to the second ring, suddenly you're at 12. If you operate the third ring, you get to 32. Well, when you get all the way out to here, 32 heads, then you're not putting more water on the fire that's burning in the target array. All you're doing is cooling down the products of combustion enough to keep additional sprinklers from activating. And one way to keep additional sprinklers from activating is to keep pumping all this additional water in. The other way is to actually make the sprinklers have a little bit higher temperature rating so that they're less responsive in the first place. When you have these high challenge rack storage fires, you've got plenty of heat to operate these 4. You've got plenty of heat really to operate these 12. You get the ones that really matter operating, but you can avoid starting to operate that third and the fourth ring and having very large design areas by using the higher temperature rated sprinklers. It's the same exact logic for using higher temperature rated sprinklers on dry systems, is to keep from having an enormous area of operation during the dry portion. This is a colorful, fancy display that I'm going to actually accelerate ahead because it shows, I mean, it's sort of a goofy thing, but it does show, if I can make it work. I can't tell if it's running or not. Maybe we'll skip over it, I'll show it at the end. But it does show the temperature profile at the ceiling or at the sprinklers when you have sort of a typical rack storage fire. It's a little long though, so, oh no, it's running, I guess we'll let it go. So here are the 4 heads that are surround the ignition location. And let's just say, the way this is treating is a little weird. Red is 500 degrees Celsius, but what you see is that that the temperature dissipates away from this first surrounding 4 rings fairly quickly prior to activation. There's no water in the simulation. You see, even with no cooling from any heads, you have fairly high temperatures around these 4. By the time you get out here, temperatures are fairly low. Well into the fire. This is like 4 or 5 times real time. So if you have 165 degree sprinklers out in this second and third row, then the likelihood that you'll operate those when they're not really needed to actually provide water to control the fire is higher than if you have a higher temperature rating. But the delay in operation of the critical 4 around the ignition location is very small because of the growth rate of these fires and the potential of these fires. And then as you get well into it, of course, then you'll start operating these heads very far out, but normally we would certainly expect to have water discharge from this point in time. Let's see if I can go to the next slide here. There we go. So we've seen this, again, the sprinkler, the select is very important in the performance that you achieve. You've seen this one as well. And here's another visual example. Traditional 5.6K sprinklers, you operated 29 in this test. I think this was one of those tests. Same test, 4 ELOs right around the ignition location. And here's the performance difference. And what's interesting is these are essentially the same thermal sensitivity. They're both standard response, both the same temperature rating. Here's the peak temperatures above the fire, gas temperatures for the traditional sprinklers and for the ELO sprinklers. Radically different performance. Now when they started looking at clearance between the top of the commodity and the ceiling, they had just a couple of tests to go by. They ran here's test 65 we've seen before, and then they ran test 101 where they, test 65 was 20 feet of storage with a 10-foot clearance. Test 101 was 15 feet of storage with a 10-foot clearance. So they held the clearance constant and just changed the storage height. They found was that at the same density there was a pretty significant difference in design area, and that's where this table comes from. It gives you the to adjust the standard curves for different storage heights. So a couple of quick rules of thumb. The higher the storage, the more challenging the fire. We know that. Increased clearance delays sprinkler operation times, resulting in larger fires at the time of operation. There are actually cases where tests have been run where the higher clearance but lower commodity height, so if you had sort of 30 feet of storage with a 45-foot ceiling as compared to 40 feet of storage with a 45-foot ceiling, proves to be a bit more challenging, the lower storage height, which is problematic because no one keeps their warehouses full. And I think that's actually one of those things we haven't addressed very well as an industry. Clearance less than the prescribed listed minimum between the sprinkler deflector and the top of the storage prohibits proper spray pattern formation, which is very important as demonstrated by those curves that demonstrate the ELOs and those very radical performance improvements when you pick good sprinklers. Well, if you pick a good sprinkler but then put obstructions that haven't been evaluated in the wrong places, then you don't have good sprinklers anymore. And the net result of all of this work is that we wind up with the curves that are in NFPA today. And really what is being proposed is just getting rid of these curves. The reason being is because they're not very well substantiated in the first place. Oops. The good news is that the loss record of operating sprinkler storage facilities protected in accordance with these curves demonstrates that not that the curves are right, but the systems that are installed in accordance with all the requirements in FBA 13 work. So even though we have a design area on the curves, but in real fires, typically successfully protected fires operate 10 sprinklers or less. That means they're operating a higher discharge density. That means that we're sort of on the lower part of the curve, and it just tends to work. It's not because those curves are so incredibly precise that they've got down to the second or third decimal place exactly how much water you need to provide the protection. Because those curves aren't very well validated, and because we constantly see people trying to sort of engineer to them to too many significant figures, let's just get rid of it. The vehicle exists for manufacturers to provide specific application control mode sprinklers for any density and any operational area that they can demonstrate at the laboratories. So if I can go out and develop the sprinkler, the magical sprinkler, that'll protect 40 feet of group A plastics at a 0.10 density, and I can take that to UL and get it listed as a specific application control mode sprinkler. Just eliminate the curves at a single point design that, particularly now that we all have to use large orbit sprinklers for storage anyway, and we take away this implied precision that just really isn't there, simplify the design process, force the manufacturers to go back and use this specific application control mode option to really prove that the sprinklers work for the application that they're intended. That's as far as I can get without James. I apologize for any stumbling that I did. I'm sure James would have been a better presenter for you, but I'd certainly be willing to take any questions or heckles you might have this time.
The fire test, you showed the fire damage and the rate why did they stop the tests? Were the fires being controlled with the fire damage that you showed, or did they run out of water, or did they just...
No, they would just decide, they would just decide. It's a very good question, because when I went back and looked at the data, today we typically run control mode tests UL for 30 minutes and then shut them down where they are. But I went back and some of those tests run for 30 minutes, and some of them run for 45, and some of them run for 90 minutes, and some of them will run for... But there wasn't any notes that said why they decided to stop them then. So,
after attending a test at UL last year, we were told that the reason we were looking at whether to stop it or not, and the 30 minutes is because they feel most areas are covered with the fire department that will have responded and should have a line inside operating in about 30 minutes. So if you keep having another head open at 35, one more at 42, one more at 47, yeah, it's still growing, and if you let it go for 3 days, yeah, you might burn up the whole warehouse, but by then you should have water on the fire from a hose stream.
what we typically see in contemporary testing is that either it works or it doesn't. After about 10, 20 minutes, either it's controlled and you're just not operating any more sprinklers and you can walk away for 3 or 4 days, and it's going to be just that way. Or after 10 or 12 minutes, you've operated 45, 50 sprinklers and it just isn't going to work. It's pretty binary as to whether a test is successful or not. I can only think of one case where it was we didn't know until the end of the 30-minute test as to whether it passed or not. And the other thing is, a lot of these tests today, we can't operate 45, 50 heads. We operate 16. So we operate 13, get that first and second ring, then you're like right on the edge of failing anyway. So you got to run out in the full 30 minutes. And I don't have a good answer as to the duration that they ran. But if you look at the sequence of events, there are periods of time where big groups of sprinklers operate, which is sort of indicative of a fire that's burning, you've got enough heads operating so that you are either wetting or just cooling everything enough to keep additional heads from operating, but you're not necessarily really controlling the fire. So that fire travels out to another part of the storage array, then you open a group of heads that are around that area, and then you have enough cooling there to keep additional heads from operating. That's sort of implied when you read the descriptions of the tests.
So they were successful in the scope of the code to control the fire. I mean, they were, even those bad tests where we burned a lot of things, they were in fact controlling the fire. Where today we're really achieving suppression with 4 heads.
Sure. I mean, the message isn't that these curves are total failures. Very much the opposite. They worked. The message really is that they worked not because they're such fabulous feats of experimental, acumen. They've just worked because of all the other things that are built into the code.
I think another way of looking at that, and a real important point on that, is that all of those curves are drawn through the point. There is no safety factor. The big bridge I just took off 35 to get here, I hope the designer and the engineer that put that together had a safety factor in. Most structural things, most design has a safety factor. You don't put it right at the failure point or right at the number. And so when I'm looking at the new sprinkler, so the old sprinkler technology we had, there really was no safety factor. A lot of people go, well, FPA 13 has all these safety factors. Yeah, there's a little one here in Hazen-Williams, little one there, but the actual curve that you're using for high pile storage, for X storage, has no safety factor. The new heads, when you're putting out or opening up 10, 5, 13 sprinklers, but still designed for 2,000 square feet, now that's actually giving you a safety factor like all the other disciplines that we work with. And so a great way of looking at it is the new technology really is bringing us something that now we can quantify a safety factor. When Dave brings a fire test to the 13 committee, and he still has the criteria as you design for 2,000 square feet, but you only open 1,000 square foot, we can go, yeah, there's kind of a safety factor of 2 in that. That's good. We never had that before.
But you also were, your safety factor was compared against the wishy-washy thing of controlling.
Oh, yeah.
Your control and my control might be different.
No, but that fire, when you ran it, opened up 5,000 square feet ahead, so they called it a 5,000 square foot design area. Whether it was controlling that, but in the time period they ran it, that's what it opened, and so.
Yeah, I mean, I think it's always been wishy-washy, and it was even wishy-washy when the committee did it. So I forget where that slide is. This slide right here. They started what they thought was the definition of control. And when they actually ran the test, they found out that they couldn't meet that definition of control, and so they developed a new definition of control. That basically, this definition of control says that the building didn't fall down.
How long do you think it'll be before they actually do away with the curves?
I think that depends on who you ask. I think even if the committee doesn't proactively take a decision to just do away with them and go to single point design, the performance improvements and efficiencies realized by using the drill mode specific application sprinklers over time will begin to make those curves less relevant. We're seeing some of that already. And as particular retailers that do a lot of this develop proprietary protection schemes and that sort of thing, that the curves become a little less and less relevant over time. But the problem is ideally someone would write a check for $10 or $12 million to go out and redo all these tests in a more rigorous fashion, knowing what we know today, and develop a new set of curves. But we haven't found any donors yet, so.
Well, when you said the single point design, though, everything I've seen so far has been lobbying for the bottom of the curve. Correct? Is that what?
Yeah, bottom of the curve.
And so, I mean, is anybody actually designing for anything other than the bottom of the curve these days?
We see the only time that and Rich probably sees a lot more plans than I do, but really where I see people designing for further up the curve is when they're working on a tank and they have a flat water supply. But
there are some retrofits where that makes a difference. There's, if you can keep the density low enough that you can go with a larger spacing, you can do 2 2 branch lines per 25-foot bay instead of 3. There are cases where certain sprinkler contractors in certain part of the country feel it's real important to be able to slide up the curve a little bit, because then that helps them shave 5% off a bid or 2% off a bid, which is just enough to get the work. There's some spots, but most of them are not real valid fire protection, safety type issues.
You know, and one of the things that's happening now is that as steel prices in particular have gone up and gone up and gone up, and pipe size drives so much cost into the projects, is that, you know, keeping the water, the volume requirements down as low as absolutely possible. At least a lot of jobs I've been involved with lately, they'll do anything to keep from having to add steel to the project just because of the cost. So like to go from a 6-inch to an 8-inch main winds up being a big cost add.
Some of the retail design densities that are in NFPA 13, they give you 2 criteria, the 4-head criteria and then this more traditional criteria.
Yeah.
Some of the fire tests I've looked at indicate the 4-head criteria, but at least in the test I looked at, don't give you any indication of the more traditional criteria. Can you comment on why they have 2 and where they come up with the second traditional criteria?
I can, but caveat that I wasn't extensively involved in the retail coalition project. I know what they were trying to do at a base level was capture some of the performance advantage, or some of the performance add that you get when you operate a small number of heads with a large K-factor sprinkler and have a very heavy, you know, a high over discharge, significant over discharge. Now, how they back down to the other criteria, I think that came from the fire test. I think they actually ran the fire tests on some sort of pressure curve, and so they, much like they did here, they had 2 points on the curve and they connected them. But that's my understanding, and I could be a little bit off there.
Well, that was what I was wondering, because the test I looked at didn't have any.
No, there isn't. You're right. On that retail coalition where they were running the .7 and the .6, in most of the fire tests, they did open up more than 4 heads.
Right.
So when that was brought forward, I kind of said, wait a minute, how can you, where do you put .6 over 2,000? You have no data point out there. It's just out in space. So under the way we normally done fire tests, if you were running at a .7 density, no matter how many sprinklers you opened, then you were at .7 over 2,000. And it was kind of a, well, how are you picking this other lower point? Then shouldn't all the other tests do that? The committee. Accepted by the committee. There was no data point out there. Fire test was run with, .7 and never opened up more than 4 heads, so they said, well, .6, sounds good.
There was no, I was under the impression that maybe it's just they intended to run these tests on a colliding density they never opened up.
They were intended to run that, but they never opened up enough heads to ever test it to see if that really made a difference.
Okay.
Thanks.
Well, between the 2 of us, you get the right answer.
Well, I was just curious,
Yeah.
as I look at the numbers, the density from the 4-head to the 2,000 square feet or whatever they're figuring, looks like it drops anywhere from a 0.08 to 0.1,
Yeah.
but it's not consistent between the tests, so I was just curious how they came up with that.
No, if you want to know a lot more on this subject, and the only reason I'm up here kind of once in a while, is the National Fire Protection Research Foundation just concluded a study on this exact subject, and the report should be available for download off their website. Shermer put it together. It's about a 60 or 70 page report. We actually, as part of the work on reviewing that report, got a lovely graph this big page. It was a reproduction copy of all those original curves and in handwriting, all the points, and you can see where the French curves have been put on them to come up with these actual curves. There's actually one copy that exists of that original, and then they just shifted it over, and you can see the French curve marks. And that's where that came from. So there's actually a copy of that in the report if you really want to see where it came from.
Good wall art.
Yep.
Thanks.
Does this conversation relate to any other areas like the light hazard, ordinary extra curves, or?
Well, no, and yes, but not really. The light and ordinary hazard, there's a lot more data out there at different points than there is for the storage stuff. The problem is that, to go burn a light hazard test, any kind of light hazard test you want to, a few $1,000s, no big deal. To go burn one of these things is, $75,000, $80,000 a pop, so you're always very data limited.
They do have some factors, some safety factors in those curves that they do not necessarily have in these.
They do, but then in other ways, there's plenty of places where they've taken those safety factors completely out. And, probably dry systems is an area where there's been very little actual retesting of dry systems. All kinds of criteria related to dry systems, but not much testing, even less than is here, to demonstrate that that criteria is acceptable. The allowance for, was it 650 or 850 gallon dry systems where you don't need to actually do the inspector's test. We've run tests with 850 gallon systems, standard systems configured at that volume that deliver water in 90, 120 seconds. And during a very reasonable fuel package, will flash the room over long before the water ever gets there. But that criteria is still in there. You can use the 60 second, you can use, well, it's changed now, but you could use the area penalty for dry systems on these curves with a 60-second water delay. But we did the 60-second test on, well, I can show you that video. We did a simulated 60-second delay, and we operated 100 heads during the dry period. So, if you want to start picking holes through all this, you certainly can. But I think the message is that even though individual parts of the standard do have these flaws, you can't argue with the fact that we're not burning down buildings every day. So I guess the sum is greater than the parts in this case. And so every part that we can improve is either more efficient, more protection.
And kind of speaking, on some experience of sitting through committee meetings and having people present fire test data, I'm on the NFPA 30 committee, and somebody comes in and says, here's and shows the video of the test, has the nice test report in front of you, and there's actually, in a lot of cases, very limited data that's in it. Is it one test? Is it two? How many times did they repeat it? Did they make changes like that? And so, there's a lot of faith that goes into accepting that data to be put into a nationally recognized standard that people are going to rely on. And I think there's times where you really aren't 100% sure. It's like that point's way out here. Why are we using here? So it's a challenge for the committees to make those decisions, but they come to a consensus and say, well, this is what the committee chooses to do on this. Because there is only limited, and to go back and test it again is another $50,000, and there just isn't that money to run repeated tests to make sure that this not only happened once, but it happened twice, and happened 3 times the same way on the test. I'm sure you see the same thing in 13.
I think it's true in every standard that involves full-scale testing. It's just so expensive to do full-scale testing that even this basic concept of understanding your reproducibility is, the 1626 test, for example, the residential test, costs $100 to run. It's probably been run 4,000 or 5,000 times easily. We've run it over 1,000 times in our labs alone. But we still don't have a good characterization of what the actual reproducibility of that test is. We feel like it's pretty good, but if you ask me to put, a probability curve around over the thing, then I couldn't do it for you.
There's another thing too with it, is that if, you may not be seeing all the data in the committee. You don't see, if they have failures, they're not bringing that forward. So So you're only seeing their successes, and if the next time they ran it, it didn't work, you don't see that.
What's that statement?
No, I think
How many failures are there per success that actually gets published?
well, not too many, or I wouldn't have a job, but at $80,000 a pop, there are.
And if they're not telling you that, then what gets into the code doesn't have that safety factor that you're talking about.
We pass about 80% of our tests. I think what is a big problem is there's lots of single tests sponsored by various people in the industry. Some organization has something that they need to run, and those tests tend to fail quite frequently. And inevitably, as soon as those tests fails, all the data gets bottled up and it never sees the light of day. And I understand why those organizations need to do that. It's sort of just the result of the society that we live in. But in terms of the engineering community really having a good data set to work with, it certainly limits, probably fully half of the fire testing that's conducted is never reported in any public way. So.
And that's really unfortunate too, because for you to know where you're going to be successful, it's very, very helpful to know where you fail.
Right.
And if you don't know where you fail, you really don't know for sure where you're going to be.
No, you learn almost nothing from a pass. You just know that you can do it. But it is a lot of fun, I will say that. Well, thank you very much. If there are any questions, or certainly if there's things that I'm not in a position to answer, as I said, I just got this yesterday, so it's a bit of a scramble, and then certainly I can give you my card, and James will be back in the office in a week or so, and I'm sure he'd be willing to talk to you directly. Thank you.
We promised 7:30, we're a couple minutes over, but I want to thank everyone for coming out, and we have a great topic for next month's meeting, so watch your emails, we'll be sending out announcements.
And anyone who has not paid please drop your name tag. Trials, doing 6 trials, just,
And I said, no, it's just, they could also be, they can't just give us a summary. They can't just give us a letter with the tables and the information that's out of the
Bear in mind, the cost is $725, but he has no obligations really much as a contract. That's true. Here's the information to the owner. That's where the problem is.